So we've covered the version of Mergesort that use n-log in actual memory. Let's see how to do it with just linear amount of actual memory. So the basic idea is the same, but instead of keep creating new arrays, vectors, we just use two vectors. So this is the entry point of this implementation of merge sort. So in order to sort A, we need to create another vector B, and in fact, B is the copy of A. So B contains exactly the same thing as A. Then we will call this recursive call. So this recursive call's meaning is we want to sort A using this as indices. So the index begin and index end, and the end is not inclusive. So it's A to 0 to A dot size minus 1. And we will be using B as auxiliary. So, and the way this recursive call works is, again, we check whether we've reached the base case with a single element. If not, then we compute the middle point in the index of the middle point in the array, and then we sort the two subarrays using this recursive call. But in this case, what we are doing is we actually sort the B part of this, or sort the B array, sort whatever pass in here, and using A as an auxiliary. So because once we do that, then B will contain the array that is sorted. So the B will, so when this is done, B will be already have the two part of B, IB from IM and IM from IE, those are already sorted. Then we just merge them into A. So this merge call will merge this first argument into the last argument, and these give the three indices, the beginning, middle, and end. So let's first take a quick look at this merge call. So we'll merge the first argument into the last argument, and the logic is essentially the same. We have three indices. So here I use the merge 2 version that we talked about before, and just filling the array A. So so this recursive call, when they need to make additional recursive call, they will switch this auxiliary and the real array to be sorted again. So what happens is at the end, when we are reaching the point where we just have two sub-elements, the two sub-elements, nothing happens, and then we'll just merge those two elements into the other array. So we are jumping back and forth between these two arrays that are given here and created here. So we'll merge two elements into the second array, and then we'll merge two and two elements from the second array into the first, and then we will merge 4 and 4 elements from the first into the second, back and forth, and so on. So all we need to figure out is which array do we start with, because we want to end up as A being sorted. So the recursive call will figure that out, and by setting B and A to be exactly the same to start with, so it doesn't really matter where we start. So we can start by copying two elements into B and merge that into A, or starting from two elements in A and then copy into B. And in fact, the different portions of the array can start at a different place. So this code ensures that even though different portion may start at different place, in the end they will all end up synchronously, so that the last step is to merging two half from B into A, and so we're done. So this is a recursive version of merge sort using big O N extra memory. And another way to do merge sort is to do bottom up iterative. So instead of recursive recall, we simply loop through the array, in fact, two arrays multiple times. So here, given the array A, we create a auxiliary array B, and then we'll the merging step size will keep doubling. So start from 1, we'll be merging 1 and 1 element together, and then we'll merge 2 and 2 together, then 4 and 4 together, then 8 and 8 together. So this step size will keep doubling until the step size is bigger than n, then we will stop. And for each fixed step size, we are going at increment of 2 times that step size, because we want to, when step is 1, we want to merge the next 2 element and then the next 2. So this indices I will increment by 2 times step. And because at the last block, maybe we don't have a fully, the last chunk may be less than the step size. So therefore, this len is computed as the mean of 2 times step and n minus I. So we start at I, and we cannot go beyond n. So this is a maximum size if we are at the end of the array. So then what we do is we just merge from A to B, so I to I plus step, and I plus step to I plus len. So most of the time, this len simply will be 2 times step. So we are essentially merging 2 segments, each of them of size step, into from A to B. And after we do this, because every time we are merging from A to B, so we need to, because we start from A, so we need to copy the sorted part, we need to copy B into A again. So this in this implementation, every level we actually do a linear cost copying. So there is it is possible to avoid this copying. So essentially you have a kind of you can think of have a reference of to 2 vectors, and then you are just keep switching them back and forth. But the code is fairly tricky to write. So this is a little bit easier to write, but it have this extra copying. This recursive version doesn't have the extra copying, but the recursive call have a little bit additional overhead, even though that's should be small enough that one doesn't need to really worry about. But you can implement Mergesort using this bottom-up iterative as well. So let's take a break here.